Hello again, people. This is the final file in the NEAP Physics 2024 Unit 3 and 4 trial exam. This is questions 11 to 17, and that'll take us to the end of it because there are only 17 questions in it. Okay, let's have a look at this. Question 11. This is about a transformer situation here. There's an AC generator there, 240 volts RMS. There is a step-up transformer here, 1 to 5, so it steps up the voltage. So the voltage is going to be 5 times bigger over here, and the current's going to be 5 times smaller. Transmission lines have got a resistance of 8 ohms, so some of the power is lost there, so the voltage is going to go down. The current stays the same. The voltage is what gets affected. And then there is a step-down transformer here, 5 to 1, and then a food center. That is basically what they tell you over here. All right. All right. The generator's output voltage is 240 volts. The appliances in the food center won't operate if the voltage supplied over here is less than 220. During the food center's busiest period, the current into the primary coil of T1, in other words, over on this side, primary, secondary, is 40 amps. Determine whether the appliances will be operational during its busiest period. So you've just got to figure out what the voltage is. Well, you know what the voltage is here is 240. What's it going to be over here? What's it going to be when it gets to here? What's it going to be when it gets to there? And if that's more than 220, then everything's fine. If it's less than 220, the appliances won't work. So this is how you do it. And this is one of those questions where the setting out and the clarity of your answer really matters, because there are several stages to this, and it's very easy to make this area here just look like the absolute mire of numbers, and where there's no obvious beginning and no obvious end, and things crossed out, and things with the wrong units, etc. Right? Have a look at this. This is how to set things out. Okay, do it well. Right, at T1, so this says at T1, so the person who's reading this knows you're talking about this. All right, on the primary side of T1, 240 volts and 40 amps. I told you that on the primary coil of T1, it's 40 amps. Okay, so on the secondary side, the voltage is going to be stepped up by a factor of 5, so 240 times 5 is 1200 volts. Current goes down by a factor of 5 to 8 amps. Done. Voltage lost in transmission. Now they know they're talking about here because you've told them. Right? Subheadings are really important in these complex things that have got multi-stages. Right? Do this. Right? Makes it way easier for the people who are marking this to find the marks. Okay, to find out how much voltage is lost, you use V equals IR for this. Right? If they ask you how much power is lost, you use that power equals I squared R. Right? But we're doing voltage here because this question is asking you how much the voltage is over here. So we don't need to muck around with power. All right, voltage equals IR. 8 is the resistance. Coincidentally, 8 is the current. So it's going to lose 64 volts. So it started at 1200. It's going to lose 64. So down here at T2, over there, and again, the person marking it knows you're talking about over here now. The voltage at the primary side is 1136 and the current is 8. And on the secondary side, the voltage goes down by a factor of 5, so it's 1136 divided by 5, which is 227.2 volts. And this is what you were trying to find out. How many volts do you get over here? It was 227. It needed to be at least 220. So you then answer the question finally. Don't do that and just say, I'm done. You're not. This is you're done. Right? This voltage is more than the 220 volts needed. Therefore, the appliances will be operational. That's the answer to the question. Okay. But I cannot emphasize too much that setting this out really clearly is going to matter. It's going to help you, and it's absolutely going to help the person who marks it. Trust me, I mark these things for a living. 12. Question 12. All right. I'm assuming you've got it in front of it in an experiment. Excuse me. There you go. There's the question and the answer together. If you want to ignore me, just pause it and read. In an experiment, beams of white light are directed at this double slit situation. They go through a darkened area. make a diffraction, an interference pattern on a screen, and point P is the central bright, which is equidistant from those holes, which means it's basically directly across from the midpoint of those holes. All right. Figure 12 shows a section of the screen, so that is literally a little bit of this zoomed in. There are colored bands between the dark bands, and each colored band consists of thin bands of the 7 colors of the rainbow, red to violet. All right. A. What is the color of the band at position P? It's going to be white. Right? And here's why. Every wavelength of light is going to create constructive interference at a path difference of 0. Right? And keep in mind that from that hole to there and from the other hole to there is the same distance. Right? So that's a path difference of 0. And so everything is going to be constructively interfering. All 7 colors of the rainbow, every single frequency of visible light is going to constructively interfere there. So they're all going to combine and they're going to make white, because that's what all the colors make. All right. That's essentially what I'm saying here. All right. Now part B, let's turn over the page. I'm going to get back to this in a second. We're going to need the diagram, I think. Oh. Part B, it says explain what the spectrum of bands on the screen indicates about the nature of light. Now, the nature of light, right? Whether it's wave or particle is what they're talking about when they say the nature of light. They're not asking you whether it's bright or colorful or pretty. It's whether it's a particle or whether it's a wave, all right? So we'll just keep this here with that question in mind. All right. So these bands, this second one, this is also constructive interference, right? This is for when the path difference, let's just go to this bit here, is when the path difference between that and that is 1 wavelength exactly. Right? Now, when the path difference was 0, they all landed on the same spot. But because violet to red, all of these different colors have got slightly different wavelengths, a difference of 1 wavelength happens at slightly different positions. And that's why to the left and to the right, the other bright bands aren't white. They're not all landing on the same spot. They're landing in slightly different spots and you get a rainbow effect. And again, that's essentially what I'm saying here, right? The bands are caused by constructive interference, path difference 1 lambda, right? The different positions of each band implies the colors have different wavelengths. Now, this question was about the nature of light. So the fact that they have different wavelengths and the fact that there's an interference pattern at all, right, is evidence for a wave-like structure of light. So that's the conclusion you have to get get the full marks for that question. It's about the nature of light being a wave. Now, part C, just going to get rid of that one, says, I'll just cross this across here. Says the table below shows some data from the experiment. Wavelength of red, wavelength of violet, distance between the slits. Calculate the distance between the violet band and the red band, X, shown in figure 12. So here's figure 12 again, that X. All right. Okay. So this is the formula you need. The delta X is the difference between 2 bands, or it's the difference between the P and there. Now, that delta X is not this X. That delta X is from there to there for violet and from there to there for red, because that's the first place that red landed and that's the second place that red landed. So that's red's delta X all the way across. But for violet's delta X, that's where it landed first, and that's where it landed with a path difference of 1. So that's violet's delta X. So you're going to calculate this for red. You're going to calculate this for violet, and then you're going to go 1 minus the other, and that will tell you how far that particular X is. It's a pity they said X. They could have said any letter for that, because it's actually not the delta X that is mentioned in this formula. They should have just said P or something, or Q, right? But that's what they mean. So you find that length, and then you find that length, and minus the 2. There you go. All right, question 13. This is one of those reasons I tell you to use the reading time really well and find the questions that are easy to do. I think this is a reasonably easy question to do, but if you get to this near the end of the exam and you've been sitting here for 2 hours anyway and you've got half an hour to go and then you look at this and you've got to read a page before you even get a question, it tends to demoralize people. All right, so I would choose to do this one fairly early. It's a reasonably simple question. Once you see the question, it's not too bad. It's but it's a lot of reading. It's a lot of taking things in, and by the time, and you don't want to get to this having done 2 hours worth of physics stuff and your brain is partially fried anyway. You want to get this one out of the way. It's 10 marks that you should get most of, right? But you're not going to get it if you're tired. So I would do this one early. All right, anyway, let's check out the situation. It's a photoelectric effect thing, right? There's the incident light shining on that panel. It's going to make some photoelectrons. They're going to go over to the collector and we're going to get a current. And we've got the voltage here that we can push current the other direction and figure out what the stopping voltage is. All right, got a voltmeter, got an ammeter. Okay, that's our 30-second look at the diagram. It's always worth doing this. Layla conducts experiments A and B, contains the following data. Okay, stop and have a good look at this. Firstly, she showed violet light. The light was not changing. The intensity was changing. So the light was getting brighter and brighter and brighter, more and more and more photons. Right? Frequencies was the same, it was always violet. Right? So the only thing changing here was the intensity, so therefore the only result that changes should be the current. And sure enough, stopping voltage was the same, current was different. Made sense. All right. Experiment B, different light. Same intensity. So all the lights were bright, but they were all different colors. Right? So the frequencies were different, so that means energy is different because E equals HF. The stopping voltages ended up being different as you'd expect, but the current would be the same. So this is making sense now at the moment. So now that you've sort of got your mindset right, you've got this experiment in your head, now we can read the questions. Okay, hang on. I'm sure there's an A here somewhere. That one says B. I think I've just got my pages. Let me just pause this for a second. Yep, as expected, I'm an idiot. I turned the wrong page. Okay, here you go. Using the experimental data. So you have to use the experimental data. Right? Explain why the wave model does not account for the photoelectric effect. Okay, best way to do this is with this, right? Okay, there's the wave model, there's the observation, and this is where you use experimental data. I quote some figures if you want to, but just as long as you refer to one of the tables or one of the experiments, that is using the experimental data. But here's what you do. The wave model would expect that a higher intensity light would lead to more energy given to the electrons, right? The brighter the light, the more energy the electrons would come off the metal plate with. However, that doesn't happen, right? This is the observation. Experiment A, first one, shows higher intensity light did not alter the stopping voltage, and hence there's no more energy to the electrons. There you go. Right. So that is using the data to explain why the wave model does not account for this photoelectric effect, right? The experiment didn't prove that right, it proved it wrong. All right, part B. Layla's colleague wishes to repeat experiment B using the same colors, same 5 colors at an intensity of 800. Now, instead of 400, the intensity is 800. Right. Explain which results would be expected to be different in Collins' experiment. Okay. You don't have to explain what has to be the same, you just have to explain what should be different. All right. Double the intensity means double the photons per second. Okay. So this is what you do. Double the intensity equals double the photons per second, and that should equal double the amount of photoelectrons per second, right? Twice as many photons hitting the plate should mean twice as many electrons coming off. And therefore the current would roughly double, all right? So just make those 3 points and that's pretty much it. And again, that's referring directly to the data. Okay. Part C. Got a graph to interpret. Layla plots a graph of the stopping voltage versus the light frequency F for experiment B. The graph includes a line of best fit as shown there. Okay. Calculate the work function of the metal. Show your working. There are a couple of ways to do this actually. You can use the gradient. You can use the gradient rise over the run, and you can figure out what the y-intercept must have been way down here somewhere. But that is a pain in the neck. This is really easy. There's a formula for this. Okay, it says calculate the work function. Use the formula for the work function. H times the threshold frequency. The threshold frequency is the x-intercept. That looks like about 3.9 to me, and that'll be fine. You can't be expected to read any more accurately than that. If you say 3.8, I reckon they'd give it to you. It's a little bit less than 4, so you wouldn't say 4, but 3.9. And you get 1.6 electron volts. Again, use the right value of H there. Oh, sorry. I'm sorry, my finger was down below there. Here's the formula. H times the threshold frequency, about 3.9 by 10 to the 14. Don't forget that. And you need to use the value of H that is in electron volts, because this, excuse me, if the stopping voltage is in volts, the energy is in electron volts. Okay, so that is the right version to use. 1.6 electron volts is what you should get. All right. Okay, part D. I've just written see my plot down here because I'm going to plot this for you. I'm going to do it on here. Right, so for part D, it says Layla performs another similar experiment. Experiment C. She uses a different metal. It requires a voltage of 0.4 volts when it's irradiated by light of a frequency of that. On figure 14, plot the whole graph for this data. You've been given one spot. 0.4 volts, 6 by 10 to the 14. Okay, so I'm going to go over to 6 by 10 to the 14. There it is. And up to 0.4 volts. There she blows. You know that all of these graphs will have the same gradient, which is Planck's constant. So we're just going to do this. There you go. Plot the graph of this data. That's it. Right. It is worth. There you go. It is worth looking at what the graph, and what sorry. Let me start that sentence again. Actually, forget that. You don't even need to know what I was going to say. It's irrelevant. Okay. 2 marks. Piece of cake. All right, back in a second. Next. 14. Okay, beams of electrons irradiate the upper layers of a crystal such that 2 of the beams reflect from 2 atoms, atom 1 and atom 2. There you go. The reflected beams travel different distances to get to the same position A on a screen as shown in figure 15, sorry. The reflected electrons of both beams travel at that speed. Atom 2 is that much further away from A than atom 1. Show that the de Broglie wavelength of the electrons is that. Now this is another question where they haven't given you a bit of information that you need to get, and they've come to the conclusion that you're going to assume this, that you're going to assume that these are, that the difference between that and that is 1 wavelength. They didn't tell you, right? Or as far as I can read, they didn't tell you. But you need to assume that the path difference there is 1 wavelength, and therefore it's constructive interference, and that therefore that difference should be a wavelength, right? But that becomes a little bit more relevant in part B. For now, all you need to do is to get the de Broglie wavelength formula, which is this one, and put all the numbers in. You've got to put the right Planck's constant in here. It's got to be the one in joules seconds, the 6.63 by 10 to the minus 34, I think it is, right? Not the other one, because that is the SI unit of Planck's constant. The other one is not an SI unit, and these are in the right SI units, so that has to be as well. And you end up getting the 1.67 by 10 to the minus 10. Okay, right, describe the behavior of the reflected electrons of both beams when they reach position A. Justify your answer. Okay, now that you know that that is their wavelength, that is half of that. And so there's a path difference there of a couple of wavelengths, of a whole number of wavelengths. So they are going to constructively interfere there. So you're going to get a bright band, I guess, or the electron version of a bright band. You're going to get a sea of electrons. But, excuse me, the other part of this answer is that they're behaving like waves. Even though they're not waves, they're electrons. They are behaving like waves because the fact that they have a de Broglie wavelength is affecting what happens at position A. So the points you need to be making are over here. They behave like waves because they have a wavelength for a start. The path difference is 2 wavelengths, right? That divided by that is 2. And therefore they undergo constructive interference at the screen. That's pretty much it to get the 3 marks. Question 15. Right, energy level diagram of a sodium atom is here. Calculate the longest wavelength that can be emitted by an electron in a transition, okay? I'm assuming you know what this is. That's ground state, and these are all the other places, the other orbitals that electrons can jump into, and if they leave that, they've been ionized. All right, longest wavelength equals lowest energy. Long wavelengths are low energy, so we need to look to find the smallest energy gap between any of these two numbers. And the smallest gap that we could find was from 3.75 to 3.61, that one there, right? Or from n equals 5 to n equals 4. They said calculate the longest wavelength, right? So having done that, having got that difference, right, 0.14, you needed to solve it for the wavelength to find out what that is, all right? So you had to firstly identify what the jump was, and keep in mind that it was emitted, right? The longest wavelength that can be emitted by an electron. It's not being absorbed, so the electron isn't going from 4 up to 5, it's going from 5 down to 4. So make that distinction. Now part B, it's another one of these annoying explain things. Explain why the energy levels of a sodium atom are described as being quantized. Right, well, it's worth describing what quantized means. Here you go. Quantization of anything is the existence of only discrete values on a continuum with other values not possible. So the amount of children that a family has is quantified, for example. You can't have 2.697 children. You can have 1 or 2 or 3 or 4, right? There are discrete values possible, and there are lots of figures between those discrete values which are not possible. That's quantizing, right? They have specific quantums. All right, so electrons in a sodium atom can only exist in specific orbits, which have a specific amount of energy. They can't have any old amount of energy. They can only have those ones that are listed. Right? Therefore, putting those two things together, electron energies are quantized. Ta-da! That's how it's done. Pretty easy. 2 questions to go. You've hung with me this long. Well done. Question 16, muons. Okay. Muons travel at a speed of 0.99 c, and they've been very nice and they've calculated the Lorentz factor for you. And they exist for that many seconds relative to their frame of reference. So according to their own watches, they last that long. Right? They have a rest mass energy of 106 mega electron volts. That means E equals mc squared. mc squared is that. Right? According to a stationary observer on Earth, how far do the muons travel before decaying? Show you're working. This is it. Excuse me. You firstly have to realize that this is the proper time, right? Because it's in their frame of reference, that is the proper time. So that goes there. Excuse me. We need to find, I'm sorry. Sorry, just need to interrupt myself there. You need to figure out what our time frame is, and it ends up being bigger than that. It's 1.59 by 10 to the minus 5 or something like that. And then use velocity equals displacement over time to find the displacement, right? The only mistake you're going to make with this is not realizing that that was the proper time, because that was in the muon's own frame of reference. Right? The only people who are going to get this wrong are people who put the 2.2 there instead of there. All right. So for part B, muons travel approximately 650 meters before decaying, as measured in their time, in their frame of reference. Now you need to figure out whether that's the proper distance or not. Right? Explain whether your answer to part A is consistent with the shorter distance measured in the muon's frame of reference. Okay, so the problem here is frame of reference. Muons are not seeing the right distance. They are seeing a contracted length of 650 meters, because that distance is through Earth's atmosphere, and the Earth's atmosphere is not traveling at 0.99 times the speed of light, but only the muons are doing that. Okay, so you need to be able to, you need to be able to sort of demarcate frames of reference here. So there's the ground, and here's a muon, and the muon's frame of reference is that. Right? Everywhere else is Earth's frame of reference. If there's a person on Earth down here, and they're measuring anything in the sky or on the mountain or the trees or whatever, all of those distances are going to be proper. All of those measurements are going to be proper. If this human being measures something in that frame of reference, that's going to be wrong according to him, right? The only things that are going to be right for the muon are the things that are in the muon's one frame of reference, and the muon is flying down here at 0.99 C. Everything else, including that distance, is not correct as measured by the muon. All right, so that 650 meters is not a proper distance. The muon is going to see this whole distance sandwiched a little bit. Right, the muon's view of this looks a bit like this. Right, it's a bit squished. The whole thing is a little bit squished, and that's not the proper distance. That's the contracted distance. All right, hang on a second. So, how do you answer that? Firstly, answer the question. It says, explain whether your answer to part A is consistent with the shorter distance. Yes, it is. Okay. The muons see a contracted length of 650 meters because the distance is through the Earth's atmosphere, and that's not in their frame of reference. The Earth's atmosphere is not moving at 0.99 C. The muons are. Right. The Earthbound observer sees the muons traveling at the proper length, but living for a dilated time span. So we don't measure time properly for the muons. We do measure the distance that they are traveling through correctly, because they are traveling through our frame of reference, through our air. All right. Part C says calculate the total energy of your muon as measured by a stationary observer on Earth. Show you're working. That's the formula, right? Without Lorentz, that's rest energy. With it, that's the total amount of energy. Okay. They gave you the rest energy in the question, 106. So just go 7.09 times 106. They gave you both of those in the question. That's a pretty easy 2 marks. All right. Final question, question 17. Here it is. And this isn't too bad at all. All right. In an experiment, let's get this done. In an experiment, a technique for determining the charge of a small test sphere is being investigated. A vacuum chamber houses a fixed sphere of a known charge, that one. And the test sphere can be placed at any position that is 10 to 60 centimeters from a fixed sphere. The distance between the centers of the spheres is measured by D, or represented by D. The test sphere consists of a sensor which registers the force acting on it. A computer program records the data. The setup is shown in here. Okay, so you basically charged that thing up. You've charged that thing up, and because they're two charged spheres, they will have a force between them. This thing can measure the force that it's feeling, and it gets recorded on the computer. That's essentially what's going on. Okay. Part A. The table below shows the values of D, etc. It says complete the table by calculating the values of 1 over D squared. I mean, this is really easy. Again, this is why you use your 15 minutes of reading time to find the easy questions. You should do this first. Right, this is easy, easy, easy. All right, so that, square it, 1 on x, put it there. Do it 4 times, you've got a mark. Right, great way to start the exam. Part B, on the axes below, plot a graph of f versus 1 on d squared. Include a point for f equals 0. Excuse me. Include the uncertainty bars of plus or minus 0.1 newtons for the f values, and draw a straight line of best fit. Even if you want to do a curve, it says draw a straight line. So again, you're a slave to the question. Make it straight. Okay, now I haven't bothered doing this because they've done a really good job in their answers, and it is well worth having a good look at this, and particularly the way they gave the marks. This is 6 marks. This is 6 fairly easy marks. You could pull this off in 3 minutes and you get 7 marks in the first 4 minutes of the exam if you did this first. All right. There's a mark for plotting the data points, obviously. There's a mark for plotting the point 0, 0, right? Because when there's no force, there'd be no distance. Right? Excuse me, or 1 on d squared would be, sorry, there would be no force, there would be an infinite distance, so 1 on d squared would be 0. 1 mark for using an appropriate scale on the vertical, another mark for using an appropriate scale on the horizontal. That's pretty obvious. 1 mark for including uncertainty bars on at least 3 of the points because they told you to do that. And a mark from drawing a straight line of best fit. Okay, so roughly what you'd expect. Okay. Finally, it says using the graph plotted in part B, so you have to use the graph or you don't get the marks. Calculate the gradient of the line of best fit, show you're working, and give the answer to 3 significant figures. Either pick 2 points that are on the line, 2 of the drawn points, the plotted points that happen to be on the line if they are on the line. Or if your line of best fit doesn't have any points on the line, then pick 2 points that were not in the table but are on the line. All right. You're calculating the gradient of the line of best fit, so your points have to be on the line. Okay, it's not approximate. You're not getting the gradient of your results in the table. You're getting the gradient of the line of best fit. Again, that's a distinction that some people miss, and every now and then, if you've got sort of points like this, and your line of best fit has gone through and touched none of them, or very few of them, some people go that one, and they do rise over the run for those 2 points. That's incorrect. That's 0 out of 2. You're getting it. This is about the line of best fit. All right. That is almost it. There is one more thing. Okay. The charge on the fixed sphere was 10 microcoulombs. Get the units right. Using the gradient, and again, you have to use the gradient. Calculate the charge of the test sphere. Now, for the gradient of this thing, the rise over the run is f over 1 on d squared. Now, if you divide it by that, that's the same as multiplying it by d squared. So the gradient is actually f times d squared. Now, if you rearrange all this, right, this is the formula for the force between 2 charged objects, which is what we've got, which is the situation we have here. And if you rearrange this, that's the distance, of course, that's d squared, right? So rearranging it, fd squared equals that. So that's the gradient. So, excuse me. So you can put the number for your gradient right there and have k and the 1 microcoulombs for one of these, and you need to solve it for the other one. So that's how it's done. That's a little bit of a trick there. This is one of those questions where a lot of people are going to get 0 because they're not even going to know how to start that one, right? But that was the trick. The gradient of that, excuse me, the gradient of that particular graph happens to be expressed in this formula, right? And you can use that fact to figure it out fairly quickly. Okay, that is it, my friends. Thank you very much for lasting this long. I'll see you in a couple of weeks.